Okay, in the previous section, I told that we can classify the vortices into eddies and vortices, and also from another point of view, into rotational vortices and irrotational vortices, and the third group is the quantum vortex. Here I just want to speak about vortices which are coherent kind of eddies. Vortices are coherent, they are stable in time. But eddies, we have large eddies and mesoscale eddies which are called meddies. Mesoscale eddies are called meddies, and small eddies, but vortices are coherent and stable. Okay, let's start from the first item, which is called the forced vortex. The other name is the rotational vortex, or solid body rotation. This is the topic of an elementary fluid mechanics and fluid statics, which is called the rigid body rotation. Consider that we have a cup of coffee here, and you stir the coffee in the cup, or you want to make a shake using a mixer, for example, banana milk shake. When you turn on the device, there is a kind of vortex in the mixer, which is called the rigid body rotation. And you see the free surface is a concave parabola. This is the free surface. This is the side view, and this one is the top view. And we have secondary flows near the bottom of the cup. And as you see, the free surface is similar to the parabola. Okay. This is the forced vortex. The name, or the forced vortex, means that in this kind of vortex, we need an external force to create this vortex. When you put on the device, when you stir the coffee in the cup, you stir that coffee. So there is an external force there. As you see, the vortex is rotational. In order to visualize the motion of fluid and the rotationality of the flow field in the forced vortex, put a piece of wood with a sign on one end, put it on the surface of the free surface of the rotating water. In this case, you will see that the motion of this visualizer, let's call it the visualizer, is something like this. This shows that the axis of this visualizer rotates, so the flow field is rotational in this case. From mathematical viewpoints, we have proved in elementary fluid mechanics that the velocity distribution in a radial direction is linear, because this is the solid body rotation, and the magnitude of the velocity vector is proportional to the first power of the distance from the center line, the axis. This is the axis, and pressure increases in the outward direction by the power of 2 of the distance from the axis. And the vorticity, which is in the k direction, k is in the unit base vector in vertical direction, is a constant multiplied by the k. This is the vorticity vector, and is parallel to the axis of rotation. Now let's compute the velocity vector. Here the omega is the capital omega is the angular velocity, which is again in the z direction. R is the position vector x, y, and z, x, y, and 0. The velocity is the cross product of the angular velocity and the position vector. It's straightforward to perform the cross product. This is the velocity vector, and also you can compute the vorticity, which is the curl of the velocity vector. Again, it's straightforward to compute the curl of this velocity field, this one. You will understand that the vorticity vector is twice the angular velocity, and the circulation, which is the integration of the velocity, the dot product of velocity and the position vector tangent to the closed curve, is a non-zero quantity here, because the vorticity vector is non-zero. So the circulation, which is the flux of vorticity, again is non-zero. This kind of the vortex is rotational because the vorticity vector is a non-zero quantity. As I told you, this kind of vortex needs an external force, and the centripetal acceleration is balanced by pressure. This is the solid body rotation, or the forced vortex, which is a rotational kind of vortex.